Hello, everyone. We're going to probably start at least a few minutes after the hour just to make sure that more people get a chance to migrate over from the LIGO talk. But welcome back. Yeah, Leo, I heard they had problems. I don't think it's my prowess. I just got really good instructions from Barry, who is unfortunately not here to receive the proper praise.
Yeah, I don't understand why they didn't have their shit together.
I mean, it did take me a little bit of fiddling, but certainly, certainly there are enough people in LIGO that if you could have been assigned to work on that for a few days. Anyway, problems happen. As I said a little while ago, as I said a little while ago, we'll wait just a couple minutes after the hour because I know that a lot of people are going to still migrate over. So I want to give Nur a large audience, so we'll wait just a few more minutes. In the meantime, Nur, can you check to see that your screen share works?
Yeah, let me check. So you can see my screen?
Can see your screen and can hear you speak. So if you'll just hang in for a few more minutes.
Okay.
Can I ask, was anybody else able to actually get into that webinar? Because it was over-registered when I tried to view it. It said it had over 500 participants, the LIGO.
Apparently I got there early enough. I was able to get in.
Ah.
But they also had problems. One of the speakers had a power outage and disappeared.
Oh, what are the chances? I've been waiting. We had some storms the other morning. I've been waiting for a lightning strike to take me out right in the middle of this, but no such bad luck.
Did you also have tornado warnings and stuff?
No, not like you had.
Okay.
Just mild rain and some lightning.
Okay.
Apparently, it's a bad weather season down here in the south of the U.S.
There's been loads of storms in Canada as well, actually. I didn't think was a thing here.
Like thunderstorms?
Yeah, and lightning and stuff.
Oh, nice.
It's just North America, I guess, in general.
An angry continent. All right. Let's not wait too much longer because we will want to have some short break before the discussion. So we can get started now. It's my pleasure to have Nur Rifat speaking on a new surrogate model. So whenever you're ready, please take it away.
Yeah, thank you. Thank you for giving me the opportunity to talk in this session. Hi, I'm Nur Rifat. I'm doing my master's at University of Dartmouth, and I've been working in a surrogate model, which is trained by a waveform, which is actually originally generated from the point particle black hole perturbation theory. So we all know that the gravitational wave emits from the black hole binary black hole system. And in our model, we covers all three phases of the IMR waveform. I mean the inspiral, merger, and ring down. So there are a few models are out there like numerical relativity, which is very popular in LIGO due to the comparable mass ratio. Even though very recently we came to know that Professor Luster's group has able to generate the waveform for the mass ratio key equal even up to 150. So there are other model. I mean the perturbation theory, which is main focus for Lisa, and it works very good for the extreme mass ratio regions. And there are a few models also other like EOB and phenomenological models, and they are have some free parameters, and they actually mainly tuned by the NR data. And there's another model which is Clues model. Alvin Chua, who's been working in this model for a long time, and it deals with the memory signals. So the Clues model actually based on the deep neural network system. And what we are working with actually the surrogate model is purely based on the machine learning based model. So the stellar black holes or the neutron star orbiting around a supermassive black hole, then it creates the memory signal. And the theory behind this is actually the black hole perturbation theory, which is linearized Einstein equation. And the code form is time-domain T-Kolsky equation. So Dr. Khanna and his group has been developing this code for a long time, almost like 10 years, and using his own GPU accelerated supercomputer at UMass Dartmouth. So in our surrogate model, we use this training data, which has been generated from this code and this machine. So why the surrogate? We know the solving a T-Kolsky equation, even after using the big super GPU computers, it takes 2 hours for a single simulation. So if you can build a surrogate, then it's going to take less than a second, even after using a very small machine like a laptop. So this is basic simple steps. What are the surrogate is? The three basic steps, I mean, the SVD, empirical interpolation, and the parametric fits. So what we are watching at this video is a nice video given by the Vijay Verma, who is a now postdoc at Caltech. These are the training data set of the waveform. We usually take the amplitudes and the phase from this waveform. Then we take the empirical interpolation. These are YOLO nodes we are watching. These are the empirical interpolation. Then you are taking the fit along this interpolation. Then we can predict the new waveforms in between the training data set. What you are watching, the brown amplitudes going through. These are the predicted one. So we'll go more details how it works. And the first step is SVD, as I said. In our model, we use the mass ratio from 3 to 10,000. There are 37 number of training waveforms. At first, we decompose into amplitude and the phases. Then we feed through the SVD. If you look at this in the right side graph, we can see these are the singular values of this amplitude basis. The first one, the singular value is more than 10 cube. If you look, and it drastically reduced down. If you go through, go up to like 9 or 10 bases, you will see the basis values. I mean, the singular value is almost like 1 or less than a 1. So after 9 or 10 bases, you can ignore all other bases. And just by taking the first 10 bases, you can reconstruct the amplitude again. So there is a huge data compression happens in this step. So if you look at this equation, which is actually nothing but a linear combination of the basis and the coefficient. So same steps also should be applied for the phases also. So when you have the amplitude and phase, then you can reconstruct the waveform. So in the previous slide, we have got the basis from the amplitude and the phase from the, from the SVD basis. So in this case, in the next step, what we have done, the empirical interpolation. So we have used the ROMPy code, reduced order modeling Python-based code, which has been developed by Chad Gale, which is also which is a postdoc at JPL. So what it does, if you have n number of bases, it will give the n node of times along the waveforms. So as we have the basis from the SVD, then from EIM, the ROMPy code, then we'll get the 10 time nodes on the amplitudes and on the base on the amplitude and also for the phases. Now, what you are watching in the right side slides, you can picture, you can see that the blue, these are yellow nodes. These are the time nodes on the of the amplitudes. So instead of having the all time nodes, if you have just these 10 time nodes, and if you give it to the ROMPy code, it can reconstruct the whole time, whole amplitude of this time series. So there is also another step of data compression happens, that instead of having the all amplitude values, we just take the 10 amplitude values, and the amplitude and the phase values. So in the previous and this time, these amplitude and the phases on these time nodes are considered as a new coefficient. So if you look at this equation, in the previous time, we have the linear combination of coefficient and the basis. This coefficient and basis are for the SVD. Now we have a new coefficient, which is A on this time, on this specific time, EIM time nodes. So we should have a new basis. So the new basis is nothing but a linear combination of the old basis. So no instruction has been changed. What we have, we just transform from one system to another system. Now, as we mentioned in earlier, that if you have the amplitude values on these time nodes, and if you give these amplitudes, specific amplitude values of these time nodes to the ROMPy code, then you'll reconstruct the whole waveform. So if we want to predict now a waveform which is not given in the training data set, so how we can do that? So for doing this, like if you look at this top right figure, then you can see that if we want to know what the amplitude could be for Q equal 4, we don't have this training data. So at first we need to know the amplitude values along these EIM time nodes. So that's why we have to do the parametric fits. So when we do the parametric fits along these time nodes, then we can predict what the value of amplitudes and also the phase on this point could be. So after knowing these cross values and then putting these values to the ROMPy code, then we can reconstruct the whole, the full time series of amplitude and also the phase. Now, if you look at here, these are the real data in the left side, top left side. This is for the amplitudes for a specific time nodes. And the x-axis, we have a mass ratio and how the data has been changing along these mass ratios. So the blue dots are actually the amplitudes, and the black dash line, these are the spline. So you can see that the exact value, you can see that we are holding out the waveform for Q equal to 2000. And this is not as a training data set. At first we are holding out from here. Then we, based on this other training data, we put the spline. Then we want to see how well they match. And we have seen that the exact value red dot and the spline value dash line, they match very well. And the difference is 6.15 10 to the minus 5. And this is for the amplitude. And the same thing happened for the phases. We can see the error we have got 1.1 for 10 to the minus 1. Now, phases are always difficult to do the fit from this experience, from our experience. And now we have done another kind of trick. Instead of putting the Q in the spline function, we have put the log Q. Then what I've got that the bendy region and the curvy region had, the bends down. So it now more looks like, if you look at the right slide, side of the plot, you can see that they more looks like a linear. So because of it's going to be more looks like a linear, so spline spline can easily predict the value right now because of it's going to be more like a linear. So the error now is improves. You can see that error in the left side was 1.14 10 to the minus 1. Now the error is 9.08 10 to the minus 4. And same thing happened also for the amplitude 10 to the minus 5 to 10 to the minus 6. Now this is the result for full surrogate. And you can see the top panel, the black one is the predicted one, the red one is the training one, and they look very good. And this is for the data Q equal 150. And we can see also in terms of, you can see the error in terms of phases and amplitudes. If you look at the middle panel, you can see the yellow and the red one, these are the phases. And if you look at the blue dot, these are the difference of phases. And you can see in the ring down piece that error is a little bit higher than the inspiral piece. And the green one and the brown one, they are the amplitude of the waveform, and the black one is actually the error of these amplitudes. So we can see that in the inspiral part, the error is less than 10 to the minus 3, and it's getting higher and higher up to the merger, and again it gets down. Now we have, these are for the single waveform. Now you can see the error for all waveforms, like from 3 to 10,000. So if you look at here in the middle panel, and in the middle panel, you can see the in the x-axis we have a mass ratio, in the y-axis we have a L2 norm error. So the marker we have the blue triangle. This is for leave one out cross validation case. So what I mean by leave one out, it means that when we are going to predict like mass ratio, for example, mass ratio 4, at the beginning we are holding out the mass ratio 4 from the training data set. Then the circuit is going to predict based on this other data set. Then we compute the error with the predict one and the hold out one. So this will give us the most honest error by doing this LOOCV. So we can have the worst error we have got from Q equal to 150, which is this one, which is close to 10 to the minus 3. And there is also surrogate error, surrogate error, which is black dot, which is model error. We can, in this case, we are not holding out or leaving out anything. So keeping the all training data set, we are just approximating all data set. And the numerical error is the plus marker, which is all related to how the training data has been computed from the perturbation theory. Now in the bottom panel, most bottom panel, we can see these are the error, also the L2 error for each mode individually. So in the middle panel, what we have seen the error is actually considering all modes, but in the bottom panel, we are watching the error for the individual modes. So you can see the error is better for the 2.2 and 2.1, and the best error we can get as the modes is getting higher and higher, and the error is also getting higher and higher. Now we have done another kind of experiment, which is NR versus MD. And if you look at this middle panel, you can see that these are the original waveform from the NR and also from the perturbation theory. From the perspective of perturbation theory, they don't look that much of bad. And this is for mass ratio Q8, and the L2 error got 7.0 10 to the minus 1. So we are planning to improve the. We are planning to done some tuning with the NR. We are trying to see what are the behind, not the real cost, I mean, at least the cost to make these things difference. We are trying to make decrease the error between this. So what we have done that in the left side, we put an alpha factor. In the left side equation, you can see that we put an alpha scaling factor with the total mass parameter. And we explore with these different values are alpha factor. We have done the optimization like how can we get the well match in between the NR and perturbation waveform for a specific alpha. So after doing this some computation, we have found after for a specific alpha we have got this waveform after for a specific scaling factor. And the L2 error we have got 1.12 10 to the minus 2, which is the most bottom panel we can see. And if we want to see the scaling factor for different mass ratio, these are shown in the most top panel, the cross marker we are watching here. cross mark we are watching here, you can see that the alpha factor is getting higher and higher and closest to 1. And this is, we are expecting the same thing, like, because in the high mass region, we're expecting that mass ratio should be, I'm sorry, the alpha factor should be closest to 1. And we can see also that the L2 AL2 error on the red marker, these are getting down as the mass ratio is getting higher and higher. I'm sorry. Sorry about that. Okay, now there's another spinning. Now the spinning MD model is we are now working with. It's not finished yet, so it's still working. So we are planning to do in the 2 different model, for the negative spin model and for the positive spin model. And for the negative spin model, we have taken the mass ratio from 3 to 10,000 and spin rates from -8 to 0, and total number of waveforms is 351. And for the positive case, for the same mass ratio, like 3 to 10,000, and the spin rate is from 0 to plus 0.8, and total number we have taken waveform taken is 351. And there are a few challenges in the spin model, like for the negative spin case, we have seen that in the ring down piece, as the spin is getting higher and higher, up to 6, these phase are getting up, but when it comes to the spin like 0.7 and 8, the phase are getting down, and it happens because of the point particle is rotating with the central black hole earlier and the later time. And you can see some of the bumpy feature in the things in the ring down portion. This is because of the mode mixing of the prograde and retrograde things. And this is why it is a little bit of difficult from the perspective of surrogate, like at least for the fit to make a model in this region. So we have come to some solution, like we restrict the EIM interpolation points to favor the sampling the inspiral part. And we also plan to do the model like positive and negative spin regions separately. And we have seen that in the 1D surrogate, spline does a very good job, but for the 2D feed, spline is not that much of good, so we have to rely on GPR. It does a very excellent job for the 2D feed and the Gaussian process integration. So the results are here. I mean, this is for the only two modes. So these are the negative spin in the left side. So we have the model error and the surrogate error and the leave one out cross validation error, and they are very, very close. And same thing happens also for the positive spin case. I mean, the cross validation error and the model error, they are very close. But you can see there are some boundary values which the error is a little bit of higher. And it happens, I can say, for most extreme cases. I mean, in sense of extreme, like when the spin is highest and the mass ratio is lowest. So for these cases, on the 5 or 6 cases, among the 351 waveforms, we have these results. Now, the 1D surrogate is publicly available right now. Hopefully, we are going to see the 2D is going to be available very soon in black hole perturbation toolkit. The summary is surrogate model successfully predicts the gravitational wave from mass ratio 3 to 10,000 with the worst case accuracy 10 to the -3 for the 1D surrogate. And the spinning case is almost done, at least for the 2-2 mode. And the main thing is it reduced time from 2 hours to less than a second. And in our case, log Q is very, very important. It increases the accuracy, and GPR for the 2D feed is important, and domain decomposition from positive and negative spin is important for getting the higher accuracy. So our plan is to add more physics like eccentricity. Tousif Islam has been working in it. And we are planning to do also for the inclination cases. And we all know that there are a lot of applications in there, like parameter estimation and test of the error. Thank you. That's it.
Well, thank you very much, Nur, for that really clear talk and for the really exciting results. We have time for questions. Yeah, Harold, go for it.
Nice talk and very good work. Thank you very much. I am still very puzzled by this alpha rescaling working so remarkably well, even for very equal masses. So seeing this plot again and also thinking about Martin's talk yesterday, I wonder, ME on this plot, is this the mass of the more compact body or the total mass? Is this
yes, the ME is actually the mass of the the central black hole. Black hole. Central black hole.
I'm never completely sure about how all these Q factors work, but it then seems like the dashed curve in the top right panel is essentially the translation between scaling by total, scaling by the primary mass versus scaling by total.
Yeah, exactly. I mean, the ME, what is given in there, this is the mass, the central black hole, which is from the definition of MD, we put in the mass of the background space-time, which is the central one. So, and the NR case, we usually keep the total mass like 1 plus 1 by Q, right? That's why from this inspiration, we are hoping that the scaling factor could be the main issue. I mean, the total mass parameter, how is defined in EMRI and how is defined in NR cases. They are not same. So that's why you're thinking maybe these cross values, this cross marker, could be the same as the dash line, which is the dash line is actually the total mass from the definition of NR, so which is 1 plus 1 by Q, but they are not same. But we inspired from here, but here it is. I mean,
yeah, not identical, but fairly close. So it explains a significant part of the deviation. Still, I'm puzzled by this amazingly good agreement.
Yeah.
Okay, we have time briefly for a question from Alex, and then we'll have to move on. Alex? We can't hear you if you're talking, Alex, even though you're unmuted. Still not hearing, I'm still not hearing anything. You may need to type your question. Yeah, it sounds like Alex has a mic problem. Alex, why don't we have the discussion in chat or in Slack, and we'll move on. So thanks once again, Nur. If you could stop screen sharing. Next up, Tousif, are you here and able to screen share?
Yeah.
Perfect.
Can you see my screen?
I can. So we have Tousif Islam speaking to us about intermediate mass black holes. So take it away when you're ready.
Okay, thank you. Hi, I'm Tousif. I'm a first-year PhD student at University of Massachusetts, Dartmouth. And in this talk, I will talk about the intermediate mass black holes with the current generation detectors, their detectability, and parameter estimation accuracy. So for this purpose, I will use the waveform model that Nur has described just now in the last talk. So for this project, here is the list of collaborators I'm working with. For the waveform models has been built by Nur, Scott, Gaurav, and Vijay. And for the detectability and parameter estimation purpose, I'm working with Scott, Carl, and Rory. Now let's talk about the intermediate mass black holes. Intermediate mass black holes are basically the missing link in between the stellar mass black holes and the supermassive black holes. They have typically masses more than 100 solar mass, and they potentially represents an early stage in the evolution of supermassive black holes. Now, till now, there has been no direct evidence for intermediate mass black holes. However, there have been some observations of ultraluminous X-ray sources, and it was claimed that they might be intermediate mass black holes, but there is no confirmation yet. Now, in terms of gravitational wave sources, a binary consisting of one intermediate mass black hole and another intermediate mass black hole is a potential source for space-based detectors such as LISA. But when we talk about ground-based detectors, the exciting sources for us would be a binary consisting of one intermediate mass black hole and one stellar mass black hole, which we generally call intermediate mass ratio inspirals, or in short, IMRI. Now, the potential hosts for IMRIs would be dense globular clusters, and the formation channels could be hierarchical mergers. So this, like the formation channel, so the point is that if you ever detect a gravitational wave signal that comes from IMRIs, then it would not only be an indirect evidence of the existence for an intermediate mass black hole, but also you would be able to shed light on their formation channel and on the evolution of how supermassive black holes form. So with this, I will move to the detectability of intermediate mass black holes. But first, in the context of Einstein telescope, which is another ground-based telescope proposed for the future, and which has the sensitivity which is at least a factor of 10 better than the advanced LIGO sensitivity. Now, in this paper by Guert and Geyer, what they have found that if they place all the sources at 6.6 gigaparsec distance from the detectors and look into four different configurations of source properties listed here. So one stellar mass black hole consisting of 1.4 and 10 solar mass, and the intermediate mass black hole have 100 and 500 solar mass. So in that case, the SNR typically ranges from 3 to 80, which is good enough to be detected in Einstein telescope. However, the problem here is that the Einstein telescope is years away from now, and this whole work has been done using a waveform model that had only the 2-2 modes, the dominant mode here. So there is no higher modes in the computation. Okay. Then we move into the detectability of the IMBH in the current generation detectors, but more in the context of the search pipelines that LIGO uses to look for binaries. So LIGO uses two different search pipelines. One is called the template-based search pipeline called the PyCBC search pipeline. So it uses the IMR, the inspiral merger ring down waveforms, which basically targets the dominant 2-2 mode of the signal. Then they have another kind of search pipeline called the coherent wave burst search pipeline. That is an unmodeled search pipeline. It looks for the excess power in the LIGO, excess power in the LIGO grids. Okay. So now in this recent study by Chandra et al., they have compared the ability of PyCBC search pipeline and the coherent wave burst search pipeline to look for IMBH, and what they have found and what they have done is that they computed the sensitive reach for different injected IMBH signals. Here in the plot, you can see that, for example, in this upper left plot here, they injected three say IMBH signals with total mass 500, 300, and 210 for different mass ratios ranging from 1 to 7. And then they tried to recover with the PyCBC and unmodeled CWB, the coherent wave burst search pipeline. And they have found that the PyCBC search pipeline performs poorly compared to the unmodeled search pipeline in terms of the IMBH injected signals. Now, this brings the question that could including the higher modes in the search pipelines can improve the detectability for IMBHs. So of course, this is still an active area of research and there is no definite answer yes, but some of the efforts could be found in this paper by Harry et al. In 2017. So with this, it is timely that we redo some of the detectability analysis, at least in the crude level, to understand where they stands in the current generation detectors with a model that has not only the dominant 2-2 mode, but also several higher modes present. For that, we use the MD surrogate waveform that has been developed here at UMass that uses the training data generated from the point particle black hole, black hole perturbation theory, and covers a mass ratio range from 3 to 10,000. So it is a non-spinning model at this point of time, but it is now being extended to the aligned spin regime. So we have several modes here. Apart from the dominant 2-2 mode, we have 2-1, 3-3, 3-2, 3-1, 4-4, 4-3, 4-2, and 5-5. So all the waveforms are 30,500 m in duration, which means that for q equal to 10, we have 32 orbital cycles, and for q equal to 10,000, we have 144 orbital cycles. Now, this model is also available through the black hole perturbation toolkit. So if anybody is interested, they can have a look there. Okay, so now we will use this model in the context of the current generation detectors and compute the signal to noise ratio. For that, we assume a network of 5 detectors, 2 LIGO detectors in Hanford and Livingstone, the Virgo detector, the Capra detector, and the upcoming LIGO India, which would join the network in a couple of years. For LIGO India network detector, we assume the advanced LIGO noise curve, and we use all available modes in our model at this point. And we set the minimum frequency to be 20 Hz, and we investigate a mass range from 200 to 1000 solar mass and mass ratio from 20 to 50. Now, note that this mass ratio from 20 to 50, that is significantly higher than the work that has been presented here at Chandra et al., or the work done by Harry to understand the detectability of intermediate mass black holes. So for our purpose, we kept all the signals at a distance of 1 gigaparsec, which is typical for the LIGO detections. And then we compute the signal to noise ratio for all of the injected signals. Now, the signal to noise ratio is given by this expression here, which is basically an overlap between the data D and the template H. For our case, the data is the injection that we create, and which is almost the same as the template. And then we also, and the SNR computation also takes care of the noise spectral density of the detector, and it goes from the detector sensitivity range F low to F high in the frequencies. So this basically tells that how loud the signal is in a particular detector. Okay. So here we show some of the results that we have got. Like in the x-axis, we show the mass range. In the y-axis, we have the SNRs, and we show the result for inclination 3 pi by 4 and orbital phase pi by 4 and 3 pi by 4. And for that, we show the results for 4 different mass ratios, Q 20, 30, 40, and 50. In solid lines, we show the result for the dominant 2-2 mode. In the dashed lines, we show the results for the higher modes. Now, if we look into these plots, there are several cases where the 2-2 mode SNR is dominant over the higher modes SNR. But once I increase the total mass, the SNR in the higher modes increases, the SNR in the 2-2 mode decreases, and at some point, the SNR in the higher modes that becomes the driving SNR of the whole system. Now, this might be a bit confusing if one looks from the perspective of a non-spinning model where the 2-2 mode is always dominant. But the point here is that we are computing the signal to noise ratio within the LIGO band. So as the mass ratio increases and the total mass increases, the signal basically moves from the LIGO band towards the LISA band. So a significant portion of the 2-2 mode that leaves out of LIGO band, but whereas some of the higher modes are still present in the LIGO band, and that translates to some cases where you have high SNR in the higher modes compared to the 2-2 mode. Now, this basically tells us that that there would be systems having significant SNR in the 2-2 mode and also in the higher modes. And if I look into the numbers here, they're like in several cases they are more than 10. Like this is very encouraging because in LIGO, basically SNR 8 to 10 can be taken as a threshold signal to noise ratio for detectability. Okay, so now here what we do is we plot the distribution of 1,000 sources randomly sampled in the mass plane, in the mass ratio plane, and with uniform distribution taken from the inclination and the orbital phase. Now the black line here that shows the signal to noise ratio threshold of 8 for LIGO detection, and then in blue we show the distribution for the 2-2 mode, in green we show the higher modes, and then we combined SNR is shown in the red curve here. Now, so the plot basically sums up the same thing, that there would be significant portion of the binaries having SNR more than 8 only in 2-2 mode, only in higher modes, and also when both are combined. So this means that if we are lucky, we would hit one such IMBH signals in the current generation detectors. Now here we show the same thing, but instead of the histogram, we show the cumulative probability. And in green, we show the probability for the 2-2 mode, in red for higher modes, and the combined one in the green. And all signals are created at 1 gigaparsec distance from the detectors. Now, the takeaway from this plot is that around 20% of the images have SNR beyond LIGO threshold only in the 2-2 modes, and the 30% images pass the SNR threshold when all modes are included. Now, after that, we take one system for mass and mass ratio. Mainly, we take the 500 solar mass and Q equal to mass ratio 20. Now, for this system, both the higher modes and the 2-2 mode has a significant SNR. So we took the system and we created the signals at 1 gigaparsec, and then we plotted the distribution over all the extrinsic parameters describing the orbital phase, the inclination, and the source location, that is generally the right accession, declination, and the polarization. Now here we show the SNR threshold of 8, and if you look into the plot, it's clear that there would be a few binaries which can be detected in principle in the LIGO band. And so then the question comes that once any such signal should be detected, we have to do parameter estimation. Now we also should note one point here, that here all the SNR computations we have assumed a uniform distribution in the masses and mass ratios, and that might not be the most correct distribution for the mass and mass ratio regime, but at least for these kind of systems, we do not have a proper understanding of how the like the masses of black hole, intermediate mass black holes, or these kind of systems look like. So as we do not have much idea, it is better to assume a uniform distribution and see where things stand instead of assuming some power law. So after that, we move into the parameter estimation regime, and because once we get one signal, we then ask the next questions, that how well we can measure the properties of the binaries accurately. So for the parameter estimation purpose, we use the gravitational wave data from the advanced LIGO Virgo detectors, and the posterior probability of the parameters theta given data D would be given by the prior probability of the parameters and the likelihood P of data given parameter. So the likelihood basically quantifies the probability of observing the data. So it models the noise in the detector as Gaussian, and depends upon a noise weighted inner product between the data and the waveform template. Now our implementation of Bayesian inference relies on the GW inference package BILB, which can be found in this paper here, and we use a nested sampler called Dynasty, which is a parallelized sampler. And for our purpose, we used 144 cores for the parameter estimation runs. Now I'll show one example of parameter estimation here. So for that we injected, so instead of the 5 detector setup, we started with the 3 detector, and in future we'd move to the 5 detector setup. So we in the 3 detector setup, we injected a signal created at a 500 megaparsec distance with a total solar mass of 600, mass ratio of Q30, inclination 3 pi by 4, orbital phase 3 pi by 4, and RA depolarization given here. Now for that, we plot the time domain signal in the upper panel here. We plot the 2-2 mode, the 3-3 mode, and the 4-4 mode. And then in the black dashed line, we basically show the point when the signal hits 20 hertz. That means that it enters the LIGO band for the 2-2 mode. Now then we plot the frequency domain waveform here, total waveform here, along with the PhDs for advanced LIGO, Virgo, and Capra. Now the SNR, the total SNR for this system is around 18. In the higher modes, we have around 15 SNR, and the SNR in 2-2 modes around 9. So it means that this particular system is a bit interesting because the higher modes are have more signal than the 2-2 modes, and also the 2-2 mode has signal which is roughly correspond to the LIGO threshold for the detectability. So with that, we move into the parameter estimation accuracy of how well we can measure. So here we show the posterior of the 2-dimension parameter estimation result for the intermediate mass ratio black hole mass. So this particular system corresponds to a mass injection value for the IMBH of around 580.65 solar mass. And once we get the posteriors from the Bayesian inference, the median is around 579.19 solar mass with error bar of 10.4 and 10.5 solar mass. Now this corresponds to an accuracy of 0.03%, which is really good. Now by accuracy we mean that the delta m of the 1D, like the 90% credible interval divided by the mass of the injection. So it would be around 20.9 divided by the injection value here, and that corresponds to the accuracy of 0.03%. Now this, for our case, the particular signal has a duration of around 15 seconds in the detector, which can be seen here. So it's more or less 15 seconds from the time it hits the 20 hertz in the LIGO band. Now we compared the results with this paper here by Wirth and Geyer in 2010, where they have done the parameter estimation using the Fisher matrix analysis for the Einstein telescope, of course. And for that, they have they have reported 2 different kinds of systems. For the system having 1.4 solar mass for the stellar mass black hole and 100 solar mass for the intermediate mass black hole, they had a total SNR of 30, and the accuracy was very small, like 0.005%. But we have to understand that it had the signal stayed in the LIGO band for around, in the Einstein band for around 291 seconds. Compared to the second system, which consists of one stellar mass of 10 solar mass and the intermediate mass black hole have a solar mass of 500, the SNR is around 30 again, and the accuracy comes to 0.05%, which is kind of comparable to the result that we are getting here. But this particular signal stays in the Einstein telescope band for 8.3 seconds. So so how long the signal stays in the detector band, that also is a factor, is a driving factor of how well you would be able to like estimate the parameters, because the more time it would be in the signal, like you'll have more information to dig. So the point here is that this is still a 2-dimensional parameter estimation in the masses of the binaries. So right now we are working on extending this to a full 9-dimension parameter estimation for spinning and non-spinning black holes, and hopefully in the next couple of weeks we will be there. So I'll start with this summary here. So the brief summary of that is the current generation detectors can potentially observe an IMRI signal consisting of an intermediate mass black hole and a stellar black hole. Such systems would likely carry significant signal to noise ratios in the higher order modes. And then the question comes in terms of detectability, that whether including the higher order modes in the LIGO search pipelines can improve the detectability of intermediate mass black holes. So this is still an open question here, and maybe this will be answered sometime in the coming years. And finally, we show that if any MD signal is detected by the current generation detectors, our model would be able to accurately infer the source properties, at least the masses of the intermediate mass black hole. Okay, so I'll stop here. So thanks for listening. So if there are questions, I'll be happy to address.
So thanks very much for that very nice talk. And I think also raising this very interesting idea that I at least had not thought about in terms of improving detectability of these signals in LIGO by including higher order modes. Unfortunately, you're a couple minutes over your time, so we're gonna have to move forward without questions, but I really encourage everyone to ask some questions in the Slack channel about this talk. So thanks again very much for that talk. And Luke, and if you can stop screen sharing, Tousif. Luca, are you able to share your screen?
Yes.
Okay.
Okay. So, can you see my screen?
We can now, yes, and we can hear you. So whenever you're ready.
Good. So, hi everyone. Thank you for being here, and thanks to the organizers for the opportunity. I am Luca Reali, an undergraduate student at the University of Milan. And today I'll talk you about this work that we recently submitted to classical and quantum gravity. This is not going to be an EMRI talk. We focused mostly on binary black holes with both black holes with comparable masses, but I hope this will be interesting to all of you anyway. So the idea is that we developed a procedure that allowed us to map the asymptotic configuration of a precessing binary black hole at infinitely large separation to the properties of its merger remnant. So let's get into the details. So let's consider a spinning binary black hole. Here we mostly focus on two spin effects. So we consider binaries where both black hole spins play an important role. So as you all know, as the two black holes orbit each other, the spins are coupled to the orbital angular momentum and precess, while the orbital separation shrinks due to the emission of gravitational waves until the two black holes finally merge, producing a remnant. As the orbital separation, in the limit where the orbital separation goes to infinity, a spinning binary black hole is completely characterized by a set of 5 variables: the mass ratio Q, the spin magnitudes of the two black holes chi1 and chi2, and it can be shown that there are these angles θ1 and θ2 infinity that are the asymptotic values of the angles between the spins of the two black holes and the orbital angular momentum as the orbital separation goes to infinity. On the other end, merger remnant is, of course, once it reaches its equilibrium state, is of course characterized by its final mass, mf, its spin magnitude, kf, and its recoil velocity, df. So what we did was basically to combine multiple layers of post-Newtonian evolutionary techniques to describe the inspiral with a recent and very accurate numerical relativity surrogate model to estimate the remnant parameters. And so I won't enter the details of the post-Newtonian techniques we used, but I'll sketch them briefly here. So the idea is that as long as the post-Newtonian approximation holds, meaning as long as we consider orbital separation way bigger than the gravitational radius of the binary, the three timescales of the systems are widely separated, meaning that the radiation reaction timescale, the typical timescale in which the orbital separation shrinks, is way bigger than the precessional period, which is in turn way bigger than the orbital period. So in the literature, this timescale separation has been widely exploited to develop basically two kinds of post-Newtonian techniques. The well-known orbit average approaches, where one basically averages quantities over the orbital period and then evolves those average quantities throughout the spiral. And the more recent precession average approach. If you want more details about this, I'll leave you to David's talk tomorrow. But basically what one does here is to double average quantities over both the orbital and the precessional period, and then to evolve those double average quantities throughout the spiral. Now, naturally, an orbit average approach is not capable of keeping track of the evolution of a binary black hole along during each single orbit. So in order to evaluate our surrogate, we need to sample randomly a parameter, the orbital phase phi, which we sample uniformly between 0 and 2 pi. In the same way, a precession average approach is not capable of keeping track of the evolution of the binary during each precession cycle. So we need to sample an additional random parameter, the precessional phase S, which again, without entering into the details, is sampled according to this probability distribution that behaves like this. It's highly peaked at the extrema of the allowed range for the precessional phase S. So to sum up, our procedure reads like this. So we consider a certain binary configuration at infinity, then we evolve it using a precession average post-Newtonian approach up to a certain threshold in the orbital separation. Here we sample the precessional phase S, and we switch to an orbit average post-Newtonian technique. We evolve the system up to another threshold, this time in the orbital frequency, just because of how the numerical relativity surrogate model works. And here we sample the orbital phase phi, and we evaluate the surrogate to compute the remnant parameters. Now, the remnant parameters are naturally affected by a fundamental uncertainty due to the sampling of these two random phases. We argue that actually any astrophysical models that aims to connect the astrophysical properties of a binary black hole at large separation with the properties of its merger remnant has to deal with this kind of uncertainties due to the huge number of precession cycle and orbits a binary black hole completes before the two black holes merge. So our procedure naturally allows us to assess the impact of these kind of uncertainties on the predictions of the remnant parameters. And here's what we found. So first of all, we consider this specific binary configuration at infinity, and then we evolve it many times, million times, using our evolutionary procedure. And each time we sampled different values of the precessional and the orbital phase, and each time we computed the corresponding remnant parameters, and then we plotted the distribution on the remnant parameter space. So as we can see, a fixed binary configuration at infinity is not mapped into a point on the remnant parameter space, but is actually mapped into a region due to the phase sampling uncertainties that we described before. And the width of this region provides an estimate of the order of magnitude of these errors over the remnant parameters, the final mass, spin, and recoil velocity. So as we can see, what we found in this case is that the final mass of the error over the mass of the remnant is quite small. I mean, is basically negligible to all practical purposes. But the error of over the final spin is quite significant, 1.4%, and the error over the recoil velocity is huge. As you can see, the recoil velocity spans all the way from 0 to 0.01 in geometrical units. And this is because the recoil velocity is heavily affected by the exact configuration of the binary when the two black holes merge, and in particular by the exact value of the orbital phase. Now, this plot has been produced by sampling over all our sources of uncertainty, but then we wanted to disentangle the various contributions, and this is what we did here, where we considered the very same binary as before, but this time we fixed the precessional phase, and we only sampled over the orbital phase. And this is the plot and this is the corresponding distribution on the whole remnant parameter space. Well, these are the projections on the different planes. And as we can see, what we obtained by fixing the precessional phase are these two loops structures. Now, the dots are obtained just by sampling also over the Gaussian errors, the numerical errors of the surrogate, but just to show that those errors are small compared to the effects that we want to study here. So as we can see, the curves are colored according to the orbital phase. So varying the orbital phase makes you move along this two-loop structure. And we can see that there is a 2π periodicity in the orbital phase, and this was somehow to be expected because the remnant parameters are periodic in the orbital phase by construction. So we see, and the orbital phase is sampled between 0 and 2π. But then we also see an approximate pi periodicity. There are two loops, right? And this is due to symmetry, because if we considered a completely symmetric binary, that is a binary black hole with equal mass and equal spin black holes, then we would have had an exact pi periodicity within the numerical errors of the surrogate. While a more generic binary like this one, for a more generic binary like this one, the pi periodicity is broken and we have a more complex two-loop structure. So this is what happens when we fix the precessional phase. But what happens if we change it? Well, we did it in this plot. So where we consider the same binary and we repeated the same procedure as before in each line, but from one line to another, we change the value of the precessional phase. So as we can see, while varying the orbital phase makes you move along these loops, varying the precessional phase makes the loop move on the remnant parameter space, gradually covering all these regions here. So these regions are actually formed by the continuous superposition of this kind of loops. And moreover, due to the shape of the probability distribution for S that is picked at the extrema, the loops with larger and smaller values of the precessional phase provide the largest contribution to the uncertainty. So this was all regarding a single binary black hole. But what if we consider a binary population? Well, that's what we did here, where we repeated the same procedure as before, as we did in the corner plot, this time considering different binary populations, so not just a single binary, varying the initial parameters, the mass ratio, the spin magnitudes, and also the spin angles, the asymptotic spin angle distributions. And what we can see is that, and then we plotted the distributions of the errors over the remnant parameters. And what we can see is that the errors change as we change the initial parameters of the binary, so they're not fixed for different binary black holes. And and we can see that we basically generalized the result we sketched before, because in general the errors on the remnant mass are quite small. The errors on the kick velocity are huge, more than unity, and the errors on the final spin are smaller but quite significant. They can reach, depending on the binary black hole, they can reach also up to 3%. And here I also highlighted some cases where these errors are really small. For example, they are small when the mass ratio is nearly 0, or when one of the spin magnitudes is nearly 0, because, as I said before, these are mostly two spins effect. So these kind of systems are well approximated with a one spin system, and so these effects are basically negligible. Finally, here we just to show more the potential of our evolutionary procedure, we used it to map for a binary population with these fixed parameters the entire θ1 infinity, θ2 infinity plane into the final mass and final spin plane. So the gray background area here is the entire allowed range on the MF-KF plane. And then we picked a sample of binaries, these colored dots, uniformly distributed on the θ1 infinity and θ2 infinity plane. And we mapped it on the KF-MF plane. And as we can see, as we said before, each dot is sent into a region of this plane due to the effects, the uncertainties we described before. And the dots are colored according to the projected effective spin of the binary, which we called Xi, but is better known in the literature as Chi effective. And we did this in order to highlight a mass spin correlation for the remnant we see here, that is due to the orbital and gap. So basically a binary black hole where with the black hole spin mostly aligned to the orbital angular momentum tend to produce a remnant with a higher spin but a lower mass, because due to the orbital and gap the merger occurs later. And this correlation is well parameterized somehow by the projected effective spin that provides a measurement of spin alignment. So to sum up, we developed a procedure that allows us to span the entire evolutionary history of precessing binary black hole, and to naturally assess the unavoidable uncertainties that any astrophysical model has to face when try to connect the properties of a binary black hole at large separation to the properties of its major remnant. And we saw that while the uncertainty over the kick velocity is enormous, and the uncertainty over the mass is basically negligible, the uncertainty over the final spin is quite significant, of order some 1, 2, or 3%. And finally, I wasn't able to talk about this here, but in the paper we also exploited our procedure to study the correlations between the merger remnant parameters and the precessional spin dynamics of the progenitor at small separation. We exploited the concept of spin morphology, and you will hear about this in greater detail in Davide's talk. But basically what we showed is that, as expected, the merger remnant parameters are heavily affected by the relative orientations of the progenitor spin, and especially on the progenitor spin of the in-plane components of the spins, and this heavily affects the way the remnant parameters distribute on the parameter space. So thank you for listening, and if you have any questions, I'll be happy to hear them.
Thank you, Luca. We have time for a question or two. Leo.
Hi, Luca. Can you hear me?
Hi. Yes.
Yes, nice talk. There's something well, actually, I have a side comment, but then an actual question. So I think I understand these loops as just being like the images of the integral tori, because the parameters or the phase space of the system, as you go to, r goes to infinity, becomes integrable. So the phase space has these integral tori, and those are what are generating these loops that you see. But anyway, so the question is related to this fact is these tori have 5 angle variables and 5 action variables, and I understand going to r goes to infinity means that the energy goes to 0. So obviously we set one of those constants of motion, the actions, to 0, but I would have thought that there would have been 4 constants of motion instead of just these 2 constants, θ1 infinity and θ2 infinity.
Okay, so you're basically asking why we are considering just these 5 parameters.
Well, I mean, Q and chi1 and chi2 are just like parameters of the system, but then θ1 and θ2 infinity are like phase space variables that are telling us whether the system, what is the action variable?
Yes, I mean, it can be shown again. I can leave you to David's talk tomorrow for the details. But basically, it can be shown that for a precessing binary black hole system at a fixed separation R, due to the presence of constant of a series of constant of motions, the precession dynamics is completely described by 5 variables, right? Q, chi1, and chi2, the total angular momentum J, and the projected effective spin psi. So this can be shown, is shown in great detail in this paper. The point is that at infinity, the total angular momentum J diverges, and so that's no longer an accurate set of variables. And again, it can be shown that you can change from that set of variable to this one, to this equivalent one. So θ1 infinity and θ2 infinity are basically an equivalent set of variable for J and psi as long as the orbital separation goes to infinity. I don't know if that's clear.
I mean, I understand this, but this doesn't completely answer my question because
maybe I didn't understand. Okay.
So Leo, I think so. I don't know if you think about it from a simpler point of view, maybe. So at finite separation, you got 6 spin degrees of freedom, so 2 vectors, six components. As you go to past infinity, the azimuthal projections of the 2 spins. So if you split into magnitude and 2 angles, so chi1, chi2, θ1, θ2, phi1, phi2, if you want. The phis, so the azimuthal projection, don't matter anymore, because I mean there are infinitely many precession cycles at large separation, but the 2 polar angles, they asymptote to constants.
No, I completely understand that there are constants of motion. In fact, there should be 5 of. Okay, sorry. One of the problems I'm having, I guess, is that I'm thinking about eccentric binaries. There are 5 constants of motion for eccentric binaries. But even still, as you take R to infinity, energy goes to 0 and angular momentum goes to infinity, but there should be some combination of them that asymptotes to a regular value.
Yes, there is. There's, I mean, one combination, something like J square minus L square over L. And then there's chi effective, which is a constant of motion at 2 p.m. Now, these 2 guys, if you want, you can map them back into θ1 infinity and θ2 infinity, which is the parameterization we used here. Yeah, exactly. I can show you the details if you want.
Yeah, okay. We should stop taking up all the time.
Yeah, I think that's probably the full time for the talk. So let me thank you again, Luca, for the nice talk. And again, there'll be more discussion tomorrow, but also, come and ask questions on the Slack about some of the particulars for this work and for the previous talk. What we're going to do now is we have scheduled a discussion starting at 11:20. Now it's 11:12 here. I think we should give ourselves a little bit longer for a break. So stay on the channel. Don't leave this channel. We'll continue the discussion on this channel. But everyone will just take a quick 15-minute break, be back and beginning around 11:30, I guess, around 11:30. And Peter will be chairing a discussion on simulations and numerical methods in the two-body problem. So talk to you all in just a little while.
As opposed
For those who may not have heard, we're going to wait till 11:30 Central, so 8 more minutes for the break, just because we got a late start on the break. All right, I hope everyone is starting to make their way back. We're going to get started in a minute here. Peter, are you here?
I am here.
Do you have some slides prepared?
I do a few.
Sure. Why don't you try screen sharing?
Okay. There we go.
Okay, I can see that. And now it's full screen very nicely. Great. All right, let's just wait another minute.
The only problem is when I have it in full screen, I can't see the participant list, so I can't see if anybody is raising their hands.
Yeah, it is. I'll let you know. I'll keep an eye on the participants.
Okay.
All right, it's 11:30. I hope everyone is here and able to hear me and semi-awake. Peter has very generously agreed to chair a discussion session on numerical methods. Please take it away, Peter.
Okay. So I thought I'd just, because I know there's lots of people who are not really doing time domain numerical simulations, I thought I might sort of give a little bit of an overview of the considerations that goes into choosing your methods and if you want to do something in the time domain. So first of all, you have to, of course, decide on your formulation. Of course, this is not a complete list here, but so I apologize if I left out your favorite. You have to choose on your formulation. Do you want to do things Lorentz gauge perturbations? Do you do Villa-Cirilli? You want to do Tucholsky or Hertz potential? Many people start in a scalar as a sandbox for code development. I know I've been doing that. Do you stick in full GR as Carlos and the people at IIT has done? Then, of course, you have to decide on your dimensionality. So, of course, you can decompose into spherical harmonics or spin wave spherical harmonics, and in principle, reduce things down in dimensionality. Or if you stay in full GR, you can, of course, have to stay in full 3+1 dimensions. So it is, of course, an issue because if, for example, in Kerr, even if you do spin wave spherical harmonics, you still have coupling between modes if you decompose into those, but you could also, as I know that Jonathan Thornburg has done in the past, I'm not really sure what his new code is doing, just decompose into M modes and do a 2+1 numerical implementation of that. Then, of course, you have to choose how you want to discretize. Do you want to use finite differencing? You want to go spectral, as we heard about earlier today, discontinuous lurking, as I've been using, or using characteristic coordinates, like double noun coordinates with the diamond stencil that was presented earlier in the Capra meeting. And of course, you have to decide on how you actually want to integrate in time. Commonly used is the Runge-Kruger methods and the method of lines, but as we heard earlier today, that might not work for all problems. And so you have to adapt to what you want to do. Boundary conditions also depends on other choice you make, not an issue for the characteristic simulations, or if you're using hyperboloidal slicings, because that takes care of all that. But otherwise, you have to worry about physical boundary conditions that have to be approximated at a finite radius. So this is just a sort of a little bit of the different choices you have to make, and of course you can do many different combinations, and that so of course that means that there's a lot of different methods in use out there. I also just wanted to take this opportunity to do a plug for my, and a little advertisement for my own code that is now part of the Black Hole Perturbation Toolkit. This was designed as a modular and easily extensible framework for implementing 1+1 dimensional equation systems. Comes with a warning that modern object-oriented Fortran is used, which means that it's probably a deterrent for some people that it's Fortran, but I hope it helps that it's actually modern and object-oriented to make things modular and nice. And I will be happy to help interested people implement new equation systems in the code if people want help. So currently we only have Scalar and Schwarzschild implemented, but Lorentz gauge and reducibility in Schwarzschild as well as Tucholsky and Kerr is underway, and will hopefully be, all of these will hopefully be added before the next Capra meeting. End of shameless self-plug.
I actually have a quick question about that, if you don't mind.
Sure.
For the Tucholsky, is this then a time domain Tucholsky code? And if so, what's the dimensionality? Is it 2+1?
This is 1+1, as the framework only supports 1+1 currently. So it will be with the Tucholsky equations decomposed into spherical harmonics, but with mode coupling.
I see. Okay.
And so here is what I thought about as possible discussion topics. Other people might have different things. We could continue discussion of codes that have been described earlier during the talks at Capra. We could maybe talk a bit about what self-force questions really require time domain codes. Are there problems out there where it could be used, where it's not used yet? And then we could ask, as a community, are we using the right methods for the right problems? And can we be better in sharing codes and helping each other? So I've been trying to get this started at least by adding my code to the Einstein tool, to the Black Hole Perturbation Toolkit. But we might also be able to do other things in order to help each other. And then I've been wondering if there's actually any hope of performing a second order calculation in the time domain. I was kind of wondering if that was a possible topic for discussion as well. So maybe I will stop full screen here so I can actually see the participation list. I think you can still see the possible topics. And of course, I'm also open for other topics that might come up that people might have they want to talk about.
Harris is asking if the code is parallel, and then Jonathan wants to speak after that.
Okay, so he's talking about the self-force 1+1.
I think so.
Yeah, okay. So currently it's only OpenMP parallelized, so shared memory parallelized. Of course, that always, if you actually write something else, that is up to the new author to actually add that in as well. There's currently no plan to make it MPI parallelizable. It hasn't really been needed yet. And who did you say had their hands up?
Jonathan Thornburg, go for it.
Thornburg, okay. Jonathan, if you're talking, we can't hear you.
On unmute there. Now can you hear me?
Yes, we can.
Okay, so I just wanted to add a couple things to what Peter has said. First of all, I wanted to thank you, Peter, for putting your code into the toolkit repository. It's really good to have more publicly available codes. And I think I said in my slides that this new code that I'm working on now, I do plan to put into the repository as soon as I'm reasonably confident that it's working correctly. It might also be a useful model for other people because it's also meant to be a pretty modular framework for doing 1+1D. Like Peter's, it's meant to be, you know, give or take a bit pluggable physics. I call it a physics system, as a collection of equations and grid functions and diagnostic routines and so on. It's nothing as fancy as Cactus or anything. I in several previous codes, I've abused C++ templates to do this. This time I've gone back and done it properly with C++ virtual functions. So if you're a Fortran person, Peter's code is probably easier to read. If you're a C or C++ person, mine might be easier to read. And I hope to have that on the toolkit this summer. It's, you know, it's always interesting to hear the sizes. Peter, about how large is your code? I mean, is it 2,000 lines, 200,000 lines? Just approximately. It's useful to get a sense of how large a piece of software this is, to get a sense of how hard it is for someone else to skim through the code and get a vague sense of what it does.
I haven't counted it recently. I think I counted at one point and it was about 10,000 at that time.
Yeah, that's it. That seems plausible for a 1+1D code. Mine is currently about 24 or 25,000 lines, but of that, about 10,000 is utility routines like linear maps and arrays and so on that don't know anything about relativity. The relativity part, 10 or 15,000 lines.
And my number of lines is also includes a lot of comments.
Yeah, that's as it should be. So anyway, I just wanted to thank you again, Peter, and to say that there should be a second fairly generic 1D code that would be easy to add physics systems to by later this summer.
That's very good news. Thank you, Jonathan.
And I'll add, I also have a backlog of the 2+1D code, for scalar field in Kerr eccentric orbits that I wrote with Barry Wardell. That code I promised to put open source some time ago and just lost track of that and all the other things. So I'll try and tidy that up and put that on the toolkit as well sometime this summer. It's on my list of projects for this summer, is to get all these past codes that I promised to open source actually available. But that code is big and complicated, and in hindsight, it grossly abused templates. So I don't know if anyone else, you need to take a very deep breath before working on that code.
Okay, thank you very much, Jonathan. Maybe before we go on, I was wondering, I was actually pretty intrigued by the method that Harris was using earlier with the collocation points there. Can I ask you something about that? Are you here?
Yeah.
Okay, so so you have this so it's a global spectral scheme then, where you just have one spectral grid, right?
Right. Yeah. Pseudospectral.
Okay, so where you have and in order to really get the good accuracy, you have to derive these jump conditions for let's say up to n/2 derivatives of your equations.
Yeah, that would be ideal, but it works even with fewer jumps or with finite differencing. It still works. It's just not as accurate.
So have you considered? I mean, this should also work in, I guess, in a discontinuous collocating scheme where you split your big domain up in elements, and you only have to do it inside one element, and you can use low order elements. So so you wouldn't need to derive as many jump conditions. Have you thought about that?
I haven't thought about that. I haven't used Galerkin methods before, so I'm not sure, but it may work. But I have to think about that.
Okay.
Yeah.
Cool. Just an idea.
Yeah. But what's nice is that you can write everything as matrix operations. So these are done in parallel automatically. For example, in Mathematica, it uses the initial math kernel libraries to parallelize them across all cores in one machine.
and it's also easy to do it on a GPU. You can just replace dot by CUDA dot essentially, and then it's done on the GPU.
So is this derivation of the jump conditions just something that can be automatized? Or do you have to think about it every time you do it?
Yeah, so that's a good question. So I know for the Reggie Wheeler equation, we can derive it analytically. So it needs to be done analytically or with computer algebra software.
Mm-hmm. Because it's quite intriguing that you can do something. You can get rid of the time-dependent coordinate transformation that I have in my code.
That was the initial goal. That's what we wanted to avoid because it's very painful.
Okay, thank you. So does anybody have any other topics to discuss, or anybody have any comments to the any of the questions I posed on as suggestions? I mean, one of these modes where, one of the Capra modes where nobody wants to say anything.
Sorry, I was just going to say, and then Jonathan, you can speak. I was just going to say, I'd be interested in actually just hearing a list of those things which time domain codes really are required for, just because I've lost track of where things stand.
Yeah. So I can talk about my own codes, and the plan there is to essentially, since we would be able to do the self-consistent evolutions, hopefully at some point soon, to be able to actually get a numerical number for the errors done in the geodesic evolutions that neglects the contribution to the self-force coming from the fact that the orbit was changing in the past. Then from my code, I can also see a use for when we get things to work in Kerr, to actually evolve, set up the code to start sort of just shortly before a resonance, and then actually evolve this code through the resonance in order to again put numerical errors on other ways of estimating the jumps in quantities across resonances. And then finally, I could also see a way of evolving with a time domain code through the plunge until the particle actually until shortly before the particle actually enters, or the small black hole enters the big black hole.
I would add all the things that I agree with, all the things Peter listed as things that you can usefully do with the time domain code. Another really useful thing, I think, is simply duplicating the same calculation that's being already done by an existing frequency domain code and working back and forth to verify you get the same numbers for gauge independent quantities. Each time, doing this for two different codes written by two different people really improves our level of confidence that we're actually computing things correctly. Ultimately, if we want, if we want various governments to give us, to give the gravitational waves community billions of euros, dollars, currency units for LISA or for third generation ground-based detectors, we've got to convince them that we in the waveform modeling community have our act together. And in the comparable mass ratio numerical relativity community, there's been an enormously successful effort to have different, a set of test simulations which different codes simulate the same binary system. And they eventually got them to the point where you lay the waveform graphs on top of each other and they look identical. We need to get our self-force to the same level where we can get predicted waveforms for an emery calculated by 2 or 3 different codes or 4 different codes and put them on top of each other and show that they're really the same. I think when we do that, we'll really improve our credibility with with funding bodies. It also, in my experience, often the act of doing this helps you to understand your own code better and sometimes even turns out bugs you didn't know about. I've had that happen in the past. Does that sort of answer the question, Aaron?
Yeah, no, that's a great answer. Leo has a hand up. I was just going to say, I would like to hear a little bit more. I thought the resonances could be treated in a 2 time scale approximation when you include the half order things, but I think I'm just making a mistake there.
No, I think you're right, but I think it would be useful to have a time domain code to sort of check how well that description in the 2
Absolutely.
it would be, and be able to just evolve through it, and would be a useful thing, I think.
Yeah, and Leo had a hand up. Maybe you wanted to say something about also scattering codes and some of the other things you've worked on in the time domain, Leo.
Yeah, so in answering your question, high eccentricity and scattering are 2 problems that are probably better done in a time domain. As to evolution, if Adam here, he can probably explain to us again why there is really only one alternative if you want to do at the moment, if you want to do a post-adiabatic calculation. And that's a 2 time scale expansion in the frequency domain. Adam, do you want to mention that again?
Sure. There's, I think, 2 reasons. One is just the level of development. So we put a lot of work into developing that framework and much less work into developing how you would do self-consistent evolution at 2nd order. The other problem with doing a self-consistent evolution at 2nd order is that you need to correctly incorporate the evolution of the black hole's mass and angular momentum. So I have a sketch of how to do that in the paper I put out on Monday, but it would definitely need significant development to actually be worked out how to do it properly. You also have a problem of getting good initial conditions for your self-consistent evolution. And so I imagine the best thing to do there would be to solve the 2 time scale equations just at 1 value of slow time and use that as your initial data for the time domain evolution. So I don't know if that answers the question. Leo?
Yes, sure. Yeah, so no, so I'm just saying it's not as simple as running your time domain code with back reaction, put back in at each time step, and that's it. There's a lot of development that's required.
Yeah, it would be a huge amount of development. And so my major worry about doing a self-consistent evolution is just, can you get good accuracy over 100,000 orbits without running it forever?
Well, as I said in my talk, I don't think we would expect to be able to do the full self-consistent inspiral with a time domain code.
Yeah, so
but I would be happy to do enough you can actually check over a reasonable long time how well the approximations actually work.
So I think there's 2 issues there. So one, I completely agree with you and Jonathan that a important reason to do it is just to make sure you get the same answer with both methods and with different codes. Obviously, it's more valuable to have totally different methods in two different codes than to have two different codes doing the same thing. But there's the other issue that there's actually no reason to think one is more accurate than the other. So the two timescale approximation is constructed such that by design, it's supposed to be uniform over the radiation reaction time. So that's really the only way we have to internally assess the accuracy. So I would think of it really as a cross-check that both methods agree with each other. There's no reason to think one is more accurate than the other. Ultimately, we'd want a totally independent thing, like comparing to the extrapolated results from numerical relativity.
So Peter, one of the things you need to worry about is to change the mass of your black hole as you go along.
Yeah, I haven't thought about how to do that, but maybe that can just be done like I do the time-dependent coordinate transformation. You just
it might be possible to just use a diabatic wave flux calculations, first order course calculations, and kind of things that Niels will be doing anyway, and he'll give you the
we can certainly measure the flux through the horizon at every single point, but then of course in principle you have to change your background metric at every single time step. But maybe you can just do it like we do with the time-dependent coordinates, where you adjust your coordinates for your equations and you keep the same grid.
I mean, in the end, the change to the black hole mass is very small. Can't that just be another dynamical degree of freedom that you evolve, follow, and place at the appropriate places in the equations of motion? I mean, maybe that's not an efficient way to carry it out, but since it stays small.
Yeah, so definitely the easiest thing would be to treat it as a first order metric perturbation rather than to alter the background. At least I think that would be the easiest thing. The problem is making sure that you don't pick up a spurious second order evolution. So if you're doing things inaccurately, then at second order, you'll have a term that's just exactly linear in time, proportional to the initial rate of change determined by your initial data. So that's actually a physically valid solution describing the linear change in the mass and spin of the black hole, but it's obviously not going to be valid over a long time scale. And if your initial data just contains something like a delta m dot or delta a dot implicitly, then your evolution is just automatically going to then pick that up. So it'll be necessary to make sure you're killing off what you don't want in second order and picking up what you do want in first order. And so I think that's a combination of good initial data and I think you can just use your calculated fluxes. If you're using hyperboloidal slicing, and you can just use your calculated fluxes at each time step to update the mass and spin.
Yeah.
Leo has a question.
Leo has his hands
up. I was going to add. I mean, I don't think I have anything. Well, or whatever. I'll just say what I wanted to say about this, which is that this, slowly varying mass, I think it will be quite similar at the level of the metric perturbations as like the, polynomially growing in time L equals 1 mode that Jonathan was talking about, controlling by, evolving a homogeneous system at the same time earlier today. So possibly Jonathan's scheme would be useful for controlling the slowly varying mass perturbation. I also wanted to say that this is kind of similar to the issue, completely unrelated to Emery's, but the issue that we have to deal with in doing this beyond GR simulation stuff, where we similarly have some polynomial in time growth of solutions that's completely expected, because what we're doing is secular perturbation theory, and we expect secular perturbation theory to have this polynomial in time breakdown. And so we're trying to understand how to renormalize it. Maybe what Jonathan is doing is the best thing that we can do. Right now, I only really understand how to do it offline as a post-processing step.
Sorry, I lost track. Who was the speaker just now?
That was Leo Stein.
Okay, sorry. Thank you.
So what about the first order sources for the second order perturbation equation, if in the time domain? Wouldn't those be difficult as well?
I think in some ways that would actually be easier than in the frequency domain.
Okay.
Maybe, I don't know. Barry tells me otherwise.
Okay.
So it becomes a different problem. So in the frequency domain, even if you're in the Lorentz gauge, where everything's pretty nice, the problem is all about mode coupling, and it's very difficult to get the the sum over products of first order modes. As you go close to the particle. In the time domain, instead, it would be, I guess, if I'm thinking of like a 2+1 implementation in Kerr, then you don't have the mode coupling problem, but you have a cancellation problem where you need to get things super accurate so that you're correctly canceling, very large numbers. And Barry tells me that these two problems are completely equivalent, so maybe there is no advantage to the time domain.
What cancellation problem? Suppose you're in 4 dimensions.
If you're in 4 dimensions, you have a 1 over r to the 4 canceling another 1 over r to the 4.
In the source.
Yeah.
Mm-hmm. Yeah, but I can see a lot of other problems when you have a non-compact source like that in the type of evolution that we are doing. So Peter, what are you doing for initial conditions?
Well, for some modes, I just evolve from 0 initial data, and then I evolve until things settle down on a geodesic motion.
Mm-hmm.
But for L equals 0, and essentially all the low L equals 0, 1, and 2, I usually use initial data from Niels Warburton's figure zooming code that he wrote in Python to get initial data set up correctly. Because for L equals 0, the way we do the things with the effective source currently in the Cellforce 1D code, when you have to sort of, if you were to turn on the start from 0 initial data, then you have to turn on the effective source smoothly, because if you just turn it on abruptly, you get non-physical modes that do not decay. But when you turn it on smoothly, you still get some unphysical modes that do decay, but for L equals 0 decay extremely slowly. And you have to do a really long evolution in order to get rid of those.
Yeah, so all of these decay properties rely very strongly on having vacuum in the asymptotic regime domains. And so my theory is that when you fill the entire space with source, that will change, and it will be much harder. You need much better control of your initial data. because you get reflections near null infinity and reflection across the horizon, along the horizon. And yeah, it seems like a very hard problem to me.
So why would you get reflections?
So now, yeah, so now you're not only in vacuum, but you have sources all the way to infinity, almost.
Yeah. I'm not sure I see why that would lead to reflections.
Hyperbolic slicing would prevent that, right?
Yeah, I think so.
But still you have sources all the way to null infinity, right?
Yeah, but they get very small.
Try to run your code with some, try to run your code with some fictitious source that runs all the way to infinity with some parallel decay and see what you get.
Okay.
So again, so you know the decay property at late time are determined by the tail of the vacuum potential, by this L time L plus 1 over R cubed. Now, if you fill the space with the sources, there will be a very strong component of this will change.
I see.
The reflection of the first order perturbation, second order waves.
Even if those sources do decay with ratios like a physical.
They will decay slowly. 1 over R squared.
Yeah.
But they will reflect very strongly. You know, even the 1 over R cube background potential reflects very strongly. Yeah,
okay. Okay, you're talking about reflections not of the boundary. It's pi plus, but just from the scattering.
Physical reflection of second order waves of the first order perturbation.
Yeah. Okay.
So again, this is potentially something, like I can see why this would be very difficult, but it's also potentially something that has an advantage over the 2 timescale method, because the 2 timescale method, at least in a generic gauge, actually breaks down at large distances. That's why we have to do this complicated matching to post-Minkowski solutions. Whereas if you're doing a self-consistent evolution, it's actually much better behaved as you go to spatial infinity. So the 2 timescale solution falls off as 1 over R squared as you go up to spatial infinity, whereas the self-consistent solution or self-consistent source should fall off significantly faster than that. Can't remember, 1 over R to the 4. It'll still fall off as 1 over R squared as you go to Scri plus, but with decreasing amplitude as you go to the past.
So yeah, so beyond these details, my concern, I guess I didn't express it very well, but it's the following. So the reason things, the initial junk decay is that it's a homogeneous perturbation superposed on your sourced equation, and homogeneous waves decay in vacuum. But here you are evolving the second order perturbation on something that's full with sources, each point in space.
Yeah. So your concern is that your junk is going to be sourcing new junk.
Yeah. And that's why I said you need a very, very careful control of your initial conditions, and you basically don't allow any junk. The junk will stay with you and potentially will actually increase and blow up.
But in principle, it should be possible to set up the simulation with the correct first order data, so that is consistent with whatever orbit you have.
You need second order data as well.
Yes.
But if you set up first order initial data like Peter's describing, then presumably the junk will only be of magnitude second order. So junk times junk cross term should be way down at fourth order, or have I counted orders wrong?
So I thought we are evolving only the second order field now.
No, you have to evolve both of them simultaneously.
So yeah, so that's a question of the architecture. So you're evolving both of them. So the second order field is a small perturbation on top. Because it would be better maybe to evolve them as a hierarchy, or simultaneously but separately, if you see what I mean, and source the, calculate first order, calculate the source at each time step, and then source the second order perturbation at each time step.
Oh yeah, that is what you. So you do this at each time step.
You're running these 2 evolutions in parallel.
Right. Yeah. Right. So yeah. So in that case, no. You have to the second. You would need the precise initial conditions for the second order perturbation, because that has its own evolution. Yeah.
I see your point, because if first order initial data has an order of unity error in its second order term.
Mm-hmm. Yeah, challenges.
We'll have it working by next year's Capra.
Good to see you, Jonathan.
Yes, well, I'd hope to come and visit you and probably Sam in Sheffield and Barry in Dublin, but combination of life and coronavirus got in the way.
Yeah, next year.
I have a question, a much less theoretical and much more practical question. This is sort of directed to Peter, but also to anybody else who's putting code in a public repository. This sounds like such a trivial issue, but it's something that I've always had trouble with. Inevitably, when I'm developing a code, there will be various things that are done in a symbolic algebra system, whatever your favorite one is. But there's also, all kinds of little calculations which you do by hand, and you jot down design notes and so on. So I've got a notebook of design notes. And this also means that, various, a function of the code will say, this code calculates something or other as per page 26 of my working notes. That means that somebody who just has the code is really handicapped in trying to understand it because they don't have your notes. Is there any better solution? What do other people do with this? What I've resorted to doing in the past is literally just, spending quite a few hours with a scanner scanning my handwritten notes, and then include a directory of scanned notes in with the code. Is there a better solution? Peter, do you have a better solution? Yes, well, LaTeX sources is fine for things that are in LaTeX, and I've usually got a document of LaTeX equations, outlining the equations. But there's always handwritten stuff which you don't want to put into LaTeX, or is too much trouble in LaTeX.
Maybe, but I mean, ultimately, if you want the code to be usable to other people, you would have to add that to your documentation.
Right.
And so that's something I still need to do. I need to actually write an overall documentation for how the ideas of the design behind the code and how everything is fitting together. I do have built-in comments that gets converted into HTML that documents all the interfaces and stuff like that. But what I still need to do myself is to actually write a proper LaTeX description of how things are supposed to fit together. And I see Harold wants to say something here.
Yeah, that's a very good question. In spec, we end up having LaTeX files scattered throughout the code. Reasonably close to the code is that depends on all these results. I think what helps there a lot is actually also writing technical papers and documenting the behind the scenes working of the code in the technical papers.
Yes.
And also what helps is if you are using a peer review code development model, that when you're having a new merge request with additions to the code, that somebody else looks at it and needs to approve the code, because others tend to be a lot harsher and demanding on actually having documentation and good comments that go along with the code you're presently trying to add.
Very good point.
If you're doing it all alone, then you're just adding it and think, oh, either I remember, or you think, oh, I'll add the notes next week, which of course will never happen.
Yeah, having a peer review, of course, does require you have some peers that are actually also working on the code and using the code and helping maintain the code. And so I'm hoping to get to that point with my code now in both in the Einstein toolkit and the black hole perturbation toolkit. Actually, currently, because of the fact that it's in the Einstein toolkit, I do need to have somebody else review my changes before they actually get added to the Git repository that the Einstein toolkit actually gets the code from.
So I have a follow-up question to Harold's comment, if I may. The idea of writing technical papers is interesting, and I'm just curious, what are the venues for these and what are the standards in the community? I'm used to seeing when a new, code hits the block, you often will see kind of a paper introducing the code, which maybe discusses the technical methods and provides some code checks, and then maybe that's separate from a physics results code. But you don't generally see a lot of such technical papers coming out of any given code base. And that's probably a function of the fact that those are not the kinds of papers that physical review or classical and quantum gravity kind of want to see. So have people solved this problem by publishing in other venues or in other places? Or are we really getting to the point where the publication venue for codes is just GitHub? And you just hope that people cite your code through Zenodo or GitHub or some appropriate thing.
So I think in my experience is that classical and quantum gravity does seem to accept these kinds of papers. And that's actually where I plan to actually at first submit the Cellforce 1D code test paper once we have it fully written. We'll see how that goes and whether they will accept it.
Another possible venue is general relativity and gravitation, which was moribund for a while, but I think it's revived now. They have in the past published code validation and comparison papers that, there has to be some relativity in it, but it can be, validating a new relativity code sort of thing.
I see Leo has his hand up. Is this about this, or should we go back to Harold before going to Leo?
Leo seems to have disappeared. His hand at least.
Oh, I don't have my hand up. I just added
Oh,
a comment.
Yeah,
Leo.
I've got to unmute myself. No, mine is entirely on a different subject, so finish with this one first. Please.
Okay, so Harold.
Yeah, Aaron, it's a difficult issue. I think another aspect is that once you have a code that's working, you want to actually use it to do science with, and you don't really care so much about documenting it and documenting its performance. As Peter says, CQG is quite happy to accept such papers, and PRD as well should be a lot more forthcoming, because code validation is important, and I think the journals recognize it slowly, and it is also, I think, a steep function of what referee you happen to run into. I'm always extremely happy to accept code validation and code documentation papers, and have done so both in PRD and CQG when I was asked to referee, because it is truly important. Otherwise, a year later, nobody really remembers and can reconstruct what a code does.
Okay, so one solution then is to always recommend Harold Pfeiffer as one of the referees, and hope the journal editor takes that suggestion.
Well, even more generally, you could be more, I never generally pick referees personally, but you could perhaps always try to make sure that you suggest a set of referees that you think are interested in such papers.
So, Leo, you had your hand up on a different subject.
Yeah, it's different. So I'll wait until you're done with this.
Are we done about this? I think we might be done.
Okay, so yeah, so back to a technical question. So I don't know how many people in the audience, besides me and Ollie, have written a Tucholsky code in the time domain 1+1, but in Schwarzschild. So yeah, evolve the Tucholsky code in Schwarzschild, the Tucholsky equation in Schwarzschild, in 1+1. And we do it in UV coordinates, so we don't have boundary conditions. And we also don't have initial conditions, or whether we don't care about those. We put zeros as usual, and we let the junk dissipate. And we found something that surprised us recently. Well, one thing we found a long time ago is that we can't do that with positive s, with s equals 2 and 1. We could do it for -1 and -2. What we found recently is that at the late time, the solution blows up. So that was so Ollie sort of that was one of the details that was kind of lost in Ollie's talk. I found it very interesting and intriguing. So, at least for a while, we weren't sure where that comes from. So what we see is a nice. So even in vacuum, if you evolve vacuum perturbation, you see the usual, ringing and parallel tail, and then at very late time, things take off with a t to the 4th tail power. So you start to get the t to the 4th blow up, so that's for negative s. For positive s, you get an exponential divergence from the beginning. Has anyone seen anything like that? Has anyone? Yeah.
I've seen the exponential thing for S positive. So my IU student last year, Sarah Skinner, did write a Tucholsky code in the Salesforce 1D infrastructure. And it worked perfectly for s equals to 0, -1, and -2. But as soon as she put in 1 or 2, there was some instability, and it just started growing in kind of in the middle of the domain.
So that we can explain exactly now. I'll get the explanation in a moment. But how long have you evolved for the negative S's?
We have, I think she evolved up to t equals 10,000 or something like that.
10,000?
There was no sign of anything growing. This was, of course, with hyperboloidal.
Okay. So that probably makes a difference.
Mm.
All right. So yeah, so it's probably effectively setting boundary conditions when you work on hyperboloidal slices, which we don't. I need to think about that. So basically, so I was looking to understand this behavior, and so it's easy to derive a general solution, analytically, the asymptotic form of the general solution near the horizon of the Tucholsky equation. So in general, in that it has two arbitrary functions of the two variables there. So one variable. And you see this exponential behavior, and also the exponent is what you see in the numerics. And you can also see that if you set the initial conditions correctly, no outgoing radiation from the path horizon, then you get rid of that kind of solutions. But because we have round-off error, and that round-off seeded that mode, and that mode then blows up exponentially. And so that's entirely consistent with the numerics. Now the s equals -2 was more of a mystery, because that was a parallel tail. So I suspected it came from null infinity. And indeed, we were able to construct a solution near null infinity that has the right behavior of this t to the 4th blow up. And again, that's a solution that is non-physical. It is incoming waves from past null infinity, and you get rid of it with boundary conditions, only we don't put boundary conditions. Say the run of error seeds it initially, and after a while, because it's only parallel, you don't see it immediately, but after a while, it takes over and everything blows up. So we understand that as well, and we're curious why other people. And the thing is that in my previous work with Paco, we never actually evolved long enough to see the parallel taking over, because we were doing circular orbits, and you only ever need to integrate over three orbits, so 2 or 3 orbits. Whereas Ollie is doing scatter orbits, and he needs to go to thousands of them. So that's the first time when we actually saw this. We think we understand that, and I don't know how to resolve it without boundary conditions. And it seems that in your scheme, with the hyperboloidal slicing, you resolve this problem, but you don't resolve the problem on the horizon.
Yeah. I was kind of just briefly looking at the equations, and I noticed that some of the coefficients in front of the first time derivative of the field seem to have the wrong sign, and I was expecting that might be the reason for the instability I saw, but I didn't look too much into detail on that.
So yeah, so I wouldn't call it instability. It's the wrong mode that you're picking up, and it's unstable. Now, if you do this analysis in Regge-Wheeler or scalar field, you see that all the solutions are non-blowing up, so they don't blow up. So Randolph, there's a physical solution which behaves whatever it wants to behave, and then there's the unphysical behavior that goes to a constant. And so you get Randolph error, of course, as well, but that remains at a very low level, also at late time. So we were sort of getting a free meal with all these years with Tucholsky and Regge-Wheeler, with scalar field and Regge-Wheeler. But as soon as you move to Tucholsky, you get this problem that the non-physical modes are not nice. So you have to do something about boundary conditions. So I'm pleased to know that the hyperboloidal slicing somehow doesn't have this problem. I don't understand why yet.
I mean, the reason why she evolved for a long time was we wanted to make sure we got the right tail behavior, and we just evolved for as long as we could.
And then another, so there's also Gaurav Khanna's code, which is sort of Cauchy evolution. Does it also have hyperboloidal slicing or not? Or does it just put boundary conditions? Do you know?
I don't know. Anybody else?
Is there anyone from Gaurav's collaboration here?
I remember when I was a grad student, when Pranesh was working with Gaurav's code, that they would only run it for segments of around 700 M long, because I think that there was an instability, and so they would stitch together these segments of around several hundreds of M's. But I don't know if that's the case anymore. That was, that was many years ago.
Yeah.
I mean, I also had an instability in my Tucholsky code when I was a grad student, but I assume that I just didn't know what I was doing.
Well, it appears, yeah, there is something about it. It's quite easy to see, actually.
But I have a question about this point, and maybe there's somebody here that is an expert and can elucidate this. So, I remember that there was this work that if you take the Tucholsky equation for just an individual field, then you can't show that there is some energy norm that the field has to be bounded by. But if you took together a system where you had the Tucholsky equation for spin s and minus s, so psi 0 and psi 4 together, that system you could show did have some energy norm that it had to satisfy. I don't really understand how, adjoining another equation to the system could allow you to show that it wouldn't blow up.
Is it like a linear combination of a function out of the field?
I don't think so. But also, this is something that I remember extremely poorly. I probably only read an abstract of a paper.
So,
So I guess
Leo,
Mike.
I was.
Okay, go ahead, Lee.
Yeah, this is Carlos.
Yep.
Yeah, I was going to comment several times during your presentation, or your presentation of your question, but you kind of were answering it as you were saying it. But so my intuition would be that the problem is in taking null coordinates and not giving boundary conditions. So this means that you have things very close to the horizon that takes a long time to come up, and those are the most that eventually blow up in your code. I didn't really evolve on null coordinates, but evolve, well, you know, the original formulation of the Regge-Wheeler was in T and R star, but you can convert them. And we always, and also the Tokowski equation, we study tails, and yeah, once you get the tails, you hit the noise that remains a round-off noise that is preserved with time. But we always took this as a Cauchy problem, right? So given initial conditions, more or less reasonable initial conditions, and then the algorithm, perhaps you flip this into null coordinates and is stable. So maybe you can do a trick like this. So trying to give reasonable boundary condition, initial conditions to a Cauchy problem, and then convert this into null initial conditions or null boundary conditions that will clean your system.
Yes. Yeah, I was just saying, you know, there are lots of advantages to working in UV. It's very convenient. But in this case, it doesn't work the way we want, and we need to be a bit more clever. And we need to think about boundary conditions. So I'm not sure initial conditions would help, but definitely boundaries. So if you do a Cauchy evolution, definitely you need boundary conditions. I agree. But I
right.
think
Also, you excise essentially by choosing limits in R star, right? R star and that plus infinity, and then you you restrict yourself to the domain of dependence of the observer, or where you evaluate the fields that
so that's
prevents
something.
you from So
that people have done, but that won't solve the problem of divergences at late time, just avoiding the boundaries.
Right.
So I think Scott Field in the chat is saying something important, which is that Gava's code actually does use colloidal slicing and runs for very long. And so again, we see that that somehow solves the problem of having to put boundary conditions. And obviously they don't see any divergence. So I need to understand why that's the case. So the way we solved it in Schwarzschild is very simply. We did a Chandrasekhar transformation, and off we moved to the Regge-Wheeler equation, which doesn't have the problem. But in Care, we don't have a Chandrasekhar transformation, unfortunately, in the time domain. And so another solution will need to be found.
So Leo, you still have your hand up. Do you have something to say?
No, it's a leftover.
Sorry.
Okay.
Oh, that's Leo. Sorry. Okay.
Yeah.
Confuse me.
So regarding the S equals positive instability, do we really need to evolve both positive and negative spin here?
No.
Okay. So I guess that's why nobody is really worrying about those S equals 2 instabilities.
Yeah, you know, there's this nice symmetry in you know, the entire Tarkovsky Newman-Pendles thing is about the symmetry between in and out and L and N, and it's not nice that it's not working the other way.
So, Lear, did you say that there are no Chandrasekhar transformations between what psi4 and Roger-Wheeler variables in the time domain for Schwarzschild?
No, for Schwarzschild, surely there is, and that's the one we're using for care, and that's the problem because you know you have the 1 over omegas there in the transformation in care. That's an important question. You know, research problem to derive something like that for care in the time domain. So Jonathan had a comment that Barry was evolving a scalar field for very long, but that's true. In the scalar field case, we don't have this problem. So the exponent of the t to the 4 is actually t to the 2s. And when s is 0, you get just a constant, so there's no blow up, and round off remains round off.
Any more comments or questions about Tucholsky?
Yeah, just to answer Scott. Thank you, Scott, for the comments. Yeah, I agree with you. Boundary conditions. Oh, my takeaway is there. Just a moment. Sorry, my Indian takeaway just arrived.
Important.
Yes, I was thanking Scott, and yes, idle boundary conditions or hyperboloidal slicing, which somehow has the effect of boundary conditions in the present case. So somehow it gets rid of the problem. I need to understand why. That's it. Thank you.
So Stephen did some work on exact radiation bound conditions. And I believe he's actually looking at this in the context of the Tucholsky equation, but it was sufficiently more challenging than the Reggie Wheeler's Reali equation. But he has some papers in the mid-2000s that may be of help as well.
Sorry, that's Stephen who?
Stephen Lau.
Oh, Stephen Lau. Okay, sorry, just want to make sure I had the right Stephen.
I mean, Stephen with a PH.
Right.
So, looks like we exhausted the Tucholsky topic. I don't know if we want to try to get some comments on some of the other topics I mentioned. Are we as a community using the right methods for the right problems? I guess that's probably difficult to answer.
Probably not.
I guess when we still have instabilities, we're probably not using the right methods. So of course, it's nice that we meet up at the yearly Capra meeting and then talk about code details and gives each other hints. But can we do better in helping each other throughout the year between Capra meetings?
So, oh, sorry, Niels should go first. I would have a hand up too.
I guess I was just going to say we have been trying to run black hole perturbation toolkit workshops, and those might be good opportunities. Those workshops are sort of split between being sort of educational and showing people how to use the code, but then having developer days where people would sort of hack on codes and share ideas. The virtual one we held this year was very successful, but in general, we've been thinking of doing basically one European and one US or North American based one per year. So that would be another opportunity as well as the Capra meetings.
That sounds like a good idea.
And I think my comment builds on that a bit. You know, my experience in LIGO is that there is a big, clunky, complicated code base with no real documentation. So you have to rely on the communal knowledge. And this works pretty efficiently because we have a Slack type channel. And whenever somebody has a technical problem and they ask it on the channel, they may not always get an answer right away, but people often monitor those things and answer. So it can be a time suck to sort of monitor that. Mm-hmm. And maybe people won't be into that, but if the BHP Toolkit workshops become, you know, kind of a culture in the community, and the Slack channel becomes a culture in the community, that's potentially a great way where someone can just, you know, drop a note in a channel and say, hey, I'm having this problem with this kind of code. Has anyone seen this blow up before? And that hits a larger audience than maybe you might email a few people you know, and it obviously can go on throughout the year. So I think the Slack channel is a great start to potentially building a community for people to help each other with code problems.
True. And also, let me do another shameless plug. There is already a Slack channel for the Cellforce 1D code.
So solutions like that, I think, right, are very workable.
Yeah. Niels again.
Yeah, I definitely agree. The Slack channel has been really great. I mean, I guess you can search through stuff there, and we actually need to probably move to a pro account so that we don't lose things after 10,000 messages. Another good thing, of course, is for people to use the issue trackers that are based on codes in the toolkit and stuff like that, because conversations can take place there, and those are well documented and stored and searchable. So that's another opportunity, you know, to discuss methods and stuff.
Mm-hmm. Yeah, the Cellforce 1D code also has, it's hosted on Bitbucket, and there's an issue tracker associated with that as well.
Do all of these codes have automatic documentation generation where the docs get pushed to some web page?
In my case, I have to generate the documentation, and then I make it available when I do it. I haven't looked into an automatic system for that.
So some toolkit stuff does. I know the Gremlin package, every time it changes, the documentation is automatically regenerated, though I'd say the documentation there is very light touch at the moment. And with the Mathematica packages, we are looking to soon have that kind of automatically generated and put on the web page, as well as being included with the package itself, obviously. So yeah, we are aiming to have these things, although they might not yet be there in all cases.
There's some past history on this, some of which has been success and some of which I'm not sure about. As most of you will know, Python has the notion of a doc string attached to each function. The SAGE project, the symbolic algebra system, the open source symbolic algebra system, has gone farther, and they've got sort of magic comments embedded in the doc string, which are the test cases for the code. And each time someone commits a new change to the code base, every night it automatically reruns all the test cases, and you get a report of which test cases are currently failing. So this ensures that in theory, this ensures that the examples in the documentation are still, don't suffer from bit rot as people change the code and stuff stops working. And my impression, looking from the outside as a very much a newbie in that community, is that this has worked pretty well. You know, the problem, but on the other hand, the problem with systems that automatically generate, you know, a formatted web page documenting your code, you know, I've seen like systems like Doxygen, is they document microscopic details, which frankly you could find out faster from reading the header files, and they don't document the big picture of, you know, does this sort of information live in that, you know, which of these eight files is most likely to contain the function that's already there that deals with this sort of problem. And that's much harder that really requires a person to create design documents and, you know, guided tour through the code. And I don't think there's any system that keeps that up to date automatically. And I will confess that I have not used any of these systems myself. I've always done it the old-fashioned way.
So I've used this Sphinx package for generating documentation for my Python code. So that's one of those things that automatically pushes the docs every time there's a new commit. And it also allows you to run doc tests in these magic, you know, if you have the correct format in your doc string, then it's also a doc test that gets run. But with Sphinx, what you can do is, you know, you can add to the documentation. So it's not purely API documentation, but you can also have like extra side narrative so that it's not just telling you about, you know, what is the third argument to this function, but, you know, what is the general idea behind this module or the code, etc.
Niels?
Yeah, so Sharon again. So the toolkit has some of this kind of continuous integration stuff built in. So some of that uses the stuff Jonathan was talking about. There is a SageMath package, the GD6GW package, and that's all integrated with Jenkins. And all the Mathematica stuff has unit tests as well that's integrated with Jenkins. And so that should stop regressions as long as the right tests are there. So people need to actually write tests. That's actually a very valuable thing for people to do. And it's all integrated as well with GitHub. So you can't actually push changes. Well, I guess you can force it to, but it'll warn you if you're trying to push a change into the master branch, which is breaking a unit test or something like that. So I agree this stuff is very important, and we're trying to include it as we build up the toolkit.
And just to emphasize, it's very difficult to cover your whole code with tests. I don't think there's any code out there where the tests cover every single line in the code.
I fairly consistently find that 30 or 40% of the total lines of code that I write are test drivers. And there's lots of different schools of thought about how to organize, you know, do the test inside or outside and so on. But the main thing is the earlier you do the testing, the better. And ideally, the test driver helps you debug, the same test driver that helped you debug the code and catch the silly typos when you were writing it, you know, in the silly cases where you wrote index I and you meant index J. Hopefully that same thing gets distributed as a test driver when you distribute the code.
So as I mentioned, there's a Slack channel for the Salesforce 1D, but maybe we need in the Slack channel sort of a more generic, just numerical methods channel where people can just discuss numerics in general instead of just one code in particular. So seems to me like we are running out of things to.
Peter, did you drop out? Can people hear me?
Yes, I could hear you.
Yes, yes, Alan. I think we lost Peter again.
We did lose Peter, and now he's joined again.
Mm-hmm.
Sorry, we lost you for a second, Peter. Peter, if you're trying.
Sorry about that, guys. My Zoom
There you
just
are.
died completely. Can you hear me now?
We can hear you.
Your Zoom is more unstable than your codes, Peter. I think that speaks well of your codes anyway.
Can you hear me?
We can hear you. Can you hear us? I'll type it. I don't think you are hearing us, Peter. But we hear you. Okay. Let's see. So I think what Peter was leading towards is we might want to think about closing off this discussion. Let's give him another opportunity to rejoin the meeting and close this off himself. But you should think if you have any last pressing questions for discussion before we finish today's discussion session. Here's Peter. Okay, Peter, are you able to hear me now?
Okay, I'm back. Can you somebody try to say something?
I'm talking, Peter. Can you hear me?
Still don't hear you. I don't know what happened there. My Zoom died and yeah.
Okay, I'll take over. Unfortunately, Peter can't hear me. Give him a huge thanks for leading the discussion, but I'll be sure to tell him. Thanks to all of you for hanging in for the whole day and for participating in the discussion. I think it's been really valuable. I think all the discussions have been very valuable so far. So we'll finish for today, and we'll see everyone bright and early, so to speak, tomorrow for the final day of the conference, which focuses a bit on spinning particles in the Emery problem, and I think has a little bit for everyone. And then a closing discussion, which will be chaired by Lior. So please do come back tomorrow, and we'll end the meeting for today. Thanks, everybody.
Thanks, Alan. Are you still here? Can I tell you something?
I'm not going anywhere.
All right.